So kicking things off, thank you so much everyone for joining. This is our first local tinyML talk. For those who are familiar, tinyML is nonprofit organization all about ultra low power machine learning at the edge, doing a lot of amazing conferences and talks from all over the world basically. And on behalf of the local group, we're really excited to welcome you to our first session. So my name is Davis. I'm one of the co-chairs here for the Montreal tinyML group, along with Sahil Gupta, Guti, and Warren Gross. You guys are on the call. They're also the co-chairs of our local committee. So big thanks also to the main committee for getting us set up here. Really excited to get into today's talk. So we'll also cover the format for today's session. We'll also cover a bit of the introduction and background material. But in general, we're going to hear from an awesome speaker named Vincent Gripon about the review of compression methods for deep convolutional neural networks. And yeah, so let's get into it here. So firstly, we'd also like to thank the sponsors for tinyML Talks. So Edge Impulse, Maxim Integrated, and SynSense, sponsors of the tinyML group. If you're interested in becoming a sponsor, you can contact information here. And also we are, because we are just getting off the ground here, still doing things virtually for now, but are looking for local sponsors in the Montreal area. If you're about machine learning, about low power sensors, definitely the group for you. Thanks to the sponsors. Also, these talks happen all the time. So to give you guys the next talk after today's, it'll be Tuesday next week. Hear from two speakers, which is the typical tinyML format. Today we have one speaker, but typically there are two. This is DSP group and Qualcomm AI. The topics are here. That'll be at 8 a.m. So same time as today's session, except 8 a.m. Pacific, so 11 a.m. Eastern time. So that'll be our next talk here. Again, so for everyone joining, there's lots of information about tinyML if you want to check it out. And now on to today. So again, on behalf of the tinyML group, we're super excited to have an awesome speaker. So Vincent's a permanent researcher at IMT-Atlantique. He's also an invited professor at Université Côte d'Azur and a visiting researcher at Mila. So for those who are aware, that university is not in Montreal, given the times right now. So Vincent's joining us from Paris. So thanks for joining this evening. But we will be doing in-person events as well. And to give a quick background, so Vincent is expert in artificial intelligence, associative memories, machine learning, efficient implementations of deep learning, and in particular, how do we compress and make these models applicable for tinyML. So we're very excited to have him speak today. And I guess without further ado, I'll also give a quick format for today. So if you have questions during the talk, please bring them up in the Q&A. You'll see a Q&A tab. I'm sure everyone's familiar with Zoom by now, but please direct the questions in the Q&A. We'll focus them and pass them on to Vincent during the presentation. And at the end, we can have further discussion. And also one quick reminder that at the end of today's session, we'll have a chance for anyone on the call to quickly give an update, a 30-second research topic, anything you want to share with the community. There will be some time for that at the end. But before that, let's let Vincent speak about his topic. We're very excited to have you. And Vincent, I'll hand it over to you now.
So thank you, Davis. Thank you everyone for joining the presentation. So my name is Vincent Gripon, and actually I'm not in Paris. I'm in Nice, but I'm still in France, so that's okay. So first, I would like to say a big thank to the organizers for inviting me today and for giving me the opportunity to present this work. As you can see on my first slide, this is a joint work with many people. I'm going to have a slide at the end where I recap the main collaborators. And as you said, Davis, I'm interested in many topics. And today I'm going to talk about different works that have been introduced in the past few years in order to compress and reduce the size and the computations required to process deep learning. So the outline is quite straightforward. So I'll start by motivating you about why you should be interested in this work. I will have a major part about compressing techniques and how they compare, and I will have a brief conclusion in the end. So, of course, when we talk about deep learning, we always start with this kind of slides where we say, okay, deep learning is fantastic because basically it solves a lot of problems that we have no alternative to solve, including, for example, recognizing objects in images, recognizing sounds, processing natural language, or even playing complex games that have some regular structure in them. And when we say that, basically, we hide the fact that to achieve this kind of outstanding performances, we need a lot of computations and a lot of memory. And just to illustrate a bit, it's typical nowadays to take a decision for an input image of about 300 by 300 pixels to require a teraflops for just one decision. It's quite typical to have models with hundreds of millions of parameters, even billions of parameters in NLP. And it's quite also usual to use a lot of GPUs to train the architectures. So of course, this is problematic for many, many communities. And just to illustrate a few, the first example is when you are interested in applications where you have constraints about the devices. So for example, you could be constrained by memory or energy, and this is a case when you have mobile devices. You would like, for example, to maximize the battery life using microcontrollers, so you cannot run too many computations. And in this case, you cannot afford to take 1 teraflops for one decision, for example. It's also the case for some applications where you have constraints about the latency. So examples are autonomous vehicles or assisted surgery. So if you need to take a decision, you cannot wait for a few seconds before you have the decision. So in this kind of applications, you have to reduce the number of computations, of course. It's not just interested for this kind of very specific applications. And it's quite fair to say that a main shortcoming of deep learning nowadays is the fact that we do not fully understand how the decisions are being made. It's very hard to visualize, it's hard to explain. And of course, the bigger the models, the more complex it is to understand how it performs. Consider, for example, that you have a model with hundreds of millions of parameters. For sure, you cannot explain the role of each parameter. But now, if you have a model with a few thousands of parameters, it becomes something that you could achieve. There's a question in the field in trying to compress architectures for better understanding and for better control over how they take their decisions. Also, it's quite fair to say that deep learning has become mostly an experimental field of research. What I mean by that is we don't have a theory of deep learning that is mature enough. And nowadays, most of the progress comes from experiments. So we have to propose a new idea, and then we have to stress the interest of this idea by using a lot of simulations. And this requires a lot of time because we have to run a lot of simulations. And of course, if we could reduce the time it needs to make an experiment, we would considerably accelerate the progress in the field. So this is also an importance for the whole field of deep learning. And finally, even if you're not into the field of deep learning, you should be concerned about these questions. Because of course, we know that data centers are more and more impactful when it comes to the global energy consumption. And data centers are more and more used to implement deep learning-like techniques. So if we want to lower the impact of data centers and deep learning, we have to work on the complexity of the solutions. Another problem that is more concerning for the policymakers is the fact that we would like to make deep learning accessible to everyone. And by that, I mean that we would like small companies, small laboratories to be able to compete in the field of deep learning. And of course, one shortcoming is the fact that you need a lot of data, but the other shortcoming is that you need a lot of computational power. And anything that brings the computational cost down is going to be beneficial to this kind of question. So we should be all concerned about making deep learning systems more accessible to these little companies and little laboratories. So these are different reasons why a lot of people have been very interested in this field of compressing deep learning architectures in the past few years. And before I get into the details of how we can achieve that, I would like first to have a few recalls about deep learning. So in my slides and in the coming experiments, a deep learning system, in my opinion, is presented as just an assembly of layers. So it's a mathematical function that is achieved by combining layers, and the combination can be very complex. It can be simply a cascade of layers, but it could be something more complex where you have different flows of information from the input to the output. But basically, this is not the part we are going to be the most concerned about. What we are going to be concerned about is really what we put into the layers of the architectures. And since we are going to conduct experiments mostly in the field of vision, we're going to be very interested in convolutional layers. So as you probably know already, there are two very important layers used in the field in computer vision. So the first one, let's say the historical one, is a fully connected layer in which you connect an input vector to an output vector by using a matrix that contains a lot of free parameters. And the main problem with fully connected layers is that they do not take into account the structure of the input. So you could have any type of input. It could be images, could be sounds, could be anything. And basically you would end up with the same kind of structure. Because of that, fully connected layers are not able to achieve very competitive performances in competitive challenges. So what we do most of the time is that we rely on convolutional layers instead, in which we exploit this very specific structure of visual inputs. And the only thing we have to understand about convolutional layers for the rest of the talk is that convolutional layers mostly come with an additional hyperparameter that is called the number of feature maps. So basically, you only have to understand that when we have a convolutional layer, we process concurrently multiple versions of an input to produce multiple versions of an output. And the number of versions of the input or the number of versions of the output are called the number of feature maps in the input and in the output. And this is something that we're going to consider a lot in reducing the size of architectures. So I'm going to present a lot of experiments in my slides, and mostly they are performed on two different data sets. So the first data set, actually there's two data sets, so it's CIFAR10 and CIFAR100. So these two data sets are very common in the field of vision. They are kind of toy data sets because they are made of tiny images. The images are 32 by 32 pixels, so it's very small. Yet they are difficult enough to be, let's say, a proxy to the difficulty you will encounter in a real-world application. For CIFAR10, you have 10 classes to distinguish from. This is an example on the slide of the classes you have in CIFAR10. And in CIFAR100, you have 100 classes to distinguish from. The other data set I'm going to use in the experiments is often referred to as ImageNet. Well, actually, ImageNet is a very large data set, and the one I'm talking about here is really a subset of ImageNet that was used in the challenge in 2012. But I'm going to say ImageNet because most of the time people just say ImageNet, even though it's not proper to say that. So these data sets are going to be used in order to stress the ability of the considered methods in achieving good accuracy while reducing and compressing the number of parameters, so the memory usage, but also the number of operations of architectures.
Hey, Vincent, just quickly here, I wanted to remind everyone that if you have questions during the talk, to please throw them in the Q&A and we can bring them up. But the one thing quickly, Vincent, is on the top of those data sets, in the search of compressed methods, do you see these as being the de facto benchmarks going forward, or do you see that not just on the model side, but on the data set side, we may also need new benchmarks in the search of compression?
Well, actually, it's a very, very, very good question. And this is something I would like to address in the end of my talk. Something that is really missing today in the field, in my opinion, is a standardized benchmark where basically you really say what you're interested in and you compete for the specific criterion, or this is something that does not really exist in the field right now. So what people are doing right now is that they are considering these benchmarks of classification on CIFAR10, CIFAR100, and ImageNet, and then they look at the performance they achieve for a given budget, let's say in the number of parameters or in the number of computations. The problem is that because there's nothing standardized about how you count, how many operations you have, or how much memory you use, basically every paper can come with its own objective. And this is something that is really missing today, in my opinion. But if that's okay with you, I would like to address this later in the talk, more in the conclusion of the talk. Okay, so now that we are ready, let's dig into the problem a bit more. So the first thing you should know is that if you're considering a specific problem, and in this slide, I'm considering the problem of the ImageNet challenge, you have a lot of different architectures to choose from. And if you look at these architectures and plot them in a compromise between the error rate they are able to achieve versus the memory they need, you obtain this kind of representation. So this representation is quite interesting because the first thing you can observe is that there seems to exist kind of a trade-off between the memory of the architecture and the error rate you can achieve. And to be more clear about that, you see that there are some architectures like ACNet that is quite big, but that is going to achieve a very, very good error rate. And at the other extreme of the curve, you have architectures that are very small, but that do not achieve the top accuracy. So this kind of Pareto optimal that you have between memory and error rate is very important, of course, to understand what we are trying to do in the field of compression. So the main question in the field of compression is, can you basically go below this red curve? Can you take an architecture and make it smaller for the same accuracy, or maybe just sacrifice a bit of accuracy but become more efficient in this compromise between memory and error rate? The second thing that we can see from this curve that is quite interesting is that there exist some architectures in the field that are not that interesting when it comes to the compromise between memory and error rate. And as you can see here, these architectures are mostly like the old ones, VGG, CafeNet, AlexNet. So these architectures were introduced before, so they did not benefit from all the ideas that came afterwards, like shortcuts, etc. And the reason why they are so bad is just because they were the initial ones to be introduced. But basically, you will see later in my slides that a lot of the time, papers that are trying to compare their methods, they are performing experiments using these very bad architectures, which is not a good idea because, of course, you could compress these architectures by a fair amount and still be less competitive than a modern architecture. So this is something that is a problem in the field, in my opinion. Just to be clear, what I drew in the previous slide, you can do the same here with the number of operations. So here you have the number of flops and the error rate, and again you see that we see this sort of a trade-off between number of operations and error rate. And again, you see that there exist some architectures that are not that efficient. It's not as clear as for the memory case, and actually, if you think about it, that's not surprising because at the time when CafeNet and AlexNet, etc., were introduced, basically the GPUs were not as fast as today, so we were kind of naturally limited by the amount of computation that we were able to make, and that's the main reason I think why, in terms of computation, you do not have that many very bad architectures in this compromise. Okay, so once I've said that, basically there's a new problem that pops up. And the problem is you have different architectures, and different architectures, not only they have different error rates, but they also have different number of computations. So now let's say that you want to compare, let's say, ResNet 18 with, why not ResNet 152. It's very hard to compare them, right? Because, I mean, they do not have the same accuracy, they don't have the same budget. So what can you say? You cannot say that one is better than the other one. And this is problematic because, of course, you would like to identify what are the architectures that are the best for a given task. So there's basically a very easy way to make these architectures comparable. And this easy way is to exploit what I said in the introduction. When you have convolutional layers, you have a given number of feature maps as input, a given number of feature maps as output. And you can basically very simply tune these parameters without having too much consequence on the overall architecture you are using. So let's say, for example, that you take all the filters you have and you divide by 2 the number of feature maps everywhere. If you do that, you're going to reduce the number of parameters by roughly a factor of 4, because basically it's a product of the input feature map with the output feature map. So you're going to considerably reduce the size of the architecture, and yet you're going to keep the same overall architecture. So this is an interesting way to design a network that is going to be less costly in terms of memory or operations, and yet bring different results. So if you do that, and here we've taken a few examples of architecture. So this time it's on CIFAR 100. And this time, just to be sure that I pointed out, this is the set accuracy that we have on the y-axis and not the error rate. So the higher, the better. So you see that we have different architectures to start from. And again, as I said before, some of these architectures, obviously, they are not interesting. So for example, here you see that MobileNet is not competitive. in this trade-off between memory and test set accuracy, because basically it requires more memory and it achieves lower accuracy than the other ones. But you cannot directly compare DenseNet with ResNet or VGG because basically they have different budgets and different accuracies. But now, if you tune the number of feature maps, you can obtain this kind of curves where now you see that it becomes quite clear that for this specific task, DenseNet is very, very challenging. It's very competitive, sorry, because basically you have a better accuracy no matter what the budget you have in terms of memory or in terms of the number of operations. So that's interesting, because it tells us that we can actually compare architectures. We just have to make sure that we have the same budget or the same accuracy and then compare which one is the best among the two we consider. The other thing interesting we can draw from this experiment is the fact that we see that, for example, with DenseNet, we can reduce by quite a large amount of times the amount of memory. So we can compress by a factor of 3, roughly, the memory, while just having a drop in accuracy that is about 1%. And this is very important to have that in mind for the slides to come afterwards. 1% accuracy is extremely expensive in terms of both memory and number of operations. So it's not surprising to be able to compress an architecture 10 times, let's say, if you have a drop in accuracy that is 5 or 6%. This is not something that is quite impressive. This is not, because basically it's just shrinking down an architecture will give you this kind of results. So of course,
one quick
yes.
question from the audience on the adjustment of the feature maps. Are you retraining from scratch as you make these adjustments, or are you retraining?
Yeah. So basically, we just when we are designing the network, we are just shrinking down the number of feature maps. So there's just one training with a smaller architectures to start from scratch.
Right. Oh.
Yeah. So this is very naive, of course, and this is something that no one would consider doing in practice, because there's a lot of other ways to shrink an architecture, but to have a lesser drop in accuracy. And one method that has been popular for quite a few years and that is quite interesting to know is what is called distillation. So distillation has been around for quite a while. I know it's a concept that has been used in the field of statistics like 20, 25 years ago. But it was introduced in the field in deep learning much more recently, of course. And mainly the idea is the following. So let's say that you have your big architecture that you've trained, and now you're going to shrink down this architecture and going to start from scratch with a smaller version of the same architecture. But when you're going to train the smaller version of the architecture, you're going to use information gathered from the big architecture to supervise the small one. So instead of just training the small one from scratch, you're going to benefit from this external help from the bigger one. So this is an idea that I think was first introduced by a group with Hinton in Toronto, in Eurips in 2014 or 15, I don't remember. And basically there's been a lot of improvements afterwards where people have said, okay, we can maybe target even intermediate representations. We can supervise intermediate representation from the big architecture to the small one. Basically, when you use this kind of techniques, you can achieve quite interesting results. So just an example of an experiment we ran in the lab. So we took a ResNet 110, which is quite a competitive competitive architecture to reduce. It's quite a good compromise between memory and accuracy. And we were able to reduce the number of parameters by a factor of roughly 4, while still maintaining the same accuracy. Actually, we even have a small increase in the accuracy. So you have to understand that this is not surprising we have a small increase in accuracy, because during training, we have many more parameters than the two initial architectures. The only thing is that at the end, we're only going to keep the small one. So when we have to just process the decision for a new input, it's going to be very fast and very cheap. Now, another thing you can do is you can simply quantize the parameters. So if you take like the standard implementation of your architecture using PyTorch or TensorFlow, whatever you want, if you do not pay attention, probably you're going to use 32-bit precision for the floats you're going to manipulate. For a long time, it has been known that that might be too much. Because basically, when we reduce the bit precision of the parameters or the activations, we see that the performance can still be quite good up to a certain amount of bits. And this is the idea of quantizing. So we ran a very small experiment where basically this time this is cipher 10. We have different architectures, and you see in the left here the evolution of the test set accuracy as a function of the number of bits we have to represent the weights in the architectures. And in the right, you have what happens when you reduce both the bit precision for the weights and for the activations. And what you can see is that you can basically reduce the number of bits from 32, the initial value, to let's say 10, 9, 8 roughly, without a single % drop in accuracy. So that's quite impressive because to be quite explicit about what we did here, we train an architecture without anything specific in mind, but at the end, we just reduce the precision of the bits and we look at what is the impact on the accuracy. And as you can see, we can reduce the number of bits by quite a fair amount before we have this drop in accuracy. Of course, if we reduce the number of bits to a very small value, then we're going to observe a dramatic drop, which is expected. So again, this is a very naive way of doing quantization. And for the past few years, a lot of contributions have been introduced in order to make the quantization happen during training so that the architecture is more robust to this drop in precision and does not suffer that much in a drop in accuracy. So
Vincent,
yes.
quick question. That's very
Yes.
interesting, and the results are interesting. In addition to quantization, because now we see hardwares in the market that can well support some of these new precisions. What about the flops rate itself? So how manipulable are those two aspects, the number of flops and then also the precision, and how manipulative is that based on the target hardware? There's been a lot of push into hardware, machine learning. What do you think about that?
So of course, there's a direct connection between the complexity, the computational complexity, and the precision of the bits for the values and the weights. With the extreme case being binary neural networks, where everything becomes very simple to compute because you don't have to multiply anymore. You just have to basically use logical gates to do your computations. So this is something also I will address later in the talk, but you could not compare directly what happens when you use these kind of methods like quantization with what I said before with distillation. Because distillation, again, it's quite clear what happens because you shrink down the architecture. But for quantization, it's way more complicated to understand exactly what is the gain in terms of complexity based on the targeted hardware. For example, on some microcontrollers, you can have a benefit up to 16 bits or 8-bit precision, but you cannot exploit that much below this value of 8-bit, and it becomes very complex to actually have some gains if you go below the 8-bit precision. Right. On some other hardware, if you, for example, you're targeting an ASIC or FPGA, of course you can benefit up to very, very small precision for the number of bits. So okay. I hope that I hope I understood your question.
The question, so these are coming from the audience as well, and then thanks everyone for adding the questions there. So if it's going to be addressed later, yeah, please feel free to go then, Vincent. And another question that came up was, does accuracy improve if you use quantization during training? Which I think you mentioned is,
yeah, this is the next slide.
Exactly.
Yeah, so basically, yeah, so the main idea of doing quantization during training was introduced in the paper by Covario from Montreal, actually. In 2015, and basically the idea is to use what is known as straight-through. So I'm sorry for my English. This is one of the most difficult things to say for a French speaker, but it's written here. I won't try it again. But basically the idea is the following. So what you do is when you do the forward pass, you're going to use the quantized version of your weights and activations, but you're going to do the backward so you're going to do the backward, let's say, computation of the gradients using the quantized version, but you're going to update the non-quantized version of your activations and your weights, sorry. So this is a very simple idea, and this is definitely a reasonable proxy to computing a gradient for weights that are discrete. And what they have shown in this paper, so the target in this paper was to completely binarize the neural networks. But of course, the same idea could be used to any precision you are targeting. And we used it in the lab for arbitrary precision. It could be anything. And this is very effective in practice. This is a very, very competitive way to introduce quantization during learning and still be able to compute a gradient and to obtain updates about the weights. So of course, as I said, this is the initial papers by Corbarrios. There's been some improvements later where people have proposed the idea of, instead of binarizing to +1, -1, which was the aim of the initial work, you could learn during training what are the values, the two values you want to keep. So they could be symmetric, but they could be non-symmetric as well. And of course, there's been a lot of works afterwards on other types of quantization where you have 3 weights, 2 to the Q weights. And as I said before, it works very, very well. And of course, the more weights you have, the more discretization steps you have, and the better are going to be your results. If you look at the papers which introduce this method, you will find this kind of table. So the first table is an extract from, I think, the papers that introduced binary weight network. And you see here something that might seem to be quite impressive. So the baseline accuracy on ImageNet is 56%. And you see that the accuracy they obtain after fully binarizing the network is going to be 56.8%. So they don't have a drop in accuracy at all. They even have an increase in accuracy. So this is very surprising, right? Because basically they are using just 1 bit for each weight instead of 32. So they have a huge compression rate. But if you remember what I said in the introduction, I said that AlexNet is not very competitive in terms of this trade-off between the memory size and the error rate. So again, you should not be surprised that we can fully binarize AlexNet and still have the same accuracy, because even by doing so, we're not competitive with other architectures found in the literature nowadays. If you look at the second table, which was introduced more recently, so they did an experiment with ResNet 18, and now you see that actually there's a drop in accuracy for using binary weight network that is quite consistent. So it's significant, again, to have 10% drop in accuracy. 10% is a large drop, so it's not surprising that you can achieve 60% by binarizing the neural network. What is interesting in this table is you see that by using three values instead of 2, we have better results, of course, and we could have added other cells as well using 4, 8, 16 possible values, and of course you would approach the full precision quite fast. To the best of my knowledge, the last papers I've seen in this field of quantization, they are able to achieve the same performance as a baseline, using a precision that is about 3 to 4 bits per layer. So this is about the state of the art today on ImageNet. One thing I would like to mention before going to the next possible method is that quantization is hard during training. And there's a very, very good drawing of that. So it's an extract from the paper. I'm sorry, this is not my figure. But basically what they've shown is that there's one reason why it works quite well to quantize both the weights and the activations. And the reason is that the range of values they take is quite similar. So you see here the range of values at the beginning of the training and at the end of the training, and you see that doesn't evolve that much. But when we're talking about the weight update, so the gradients that are computed and that are going to be added to the weights during training, you see that they have a different scale, completely different scale. So now, if you want to represent all these values using the same range, the same bits representation, of course, it's going to be very hard because you have so many orders of magnitude to represent. And this is a very, very difficult problem addressed in the community. So for the past 2 years, we've seen a couple of papers that really try to do the training with quantized version of the weights and activations. And to the best of my knowledge, it's very hard to go below 8 bits. And it's even not completely 8 bits. Sometimes they use 16 bits for some operations and 8 bits for other operations. This is, I think, the best we can achieve nowadays of quantization during training.
So
yes,
Vincent, before on precision, because it's a big topic in itself. So one question was, are you doing normalization to keep the value between -1 and 1? So using 1 bit for integer and remaining bits for fractional parts?
Yeah, this is well, we can do whatever we want, but
Right.
in most cases, what people are doing is that they are just quantizing to obtain integer representation. So they just compute using integers. But of course, you have other works where they do things differently. For example, you have works that are interested in non-uniform quantization. So for example, they use clustering techniques to find 16, 20 possible values for each weight. And then they are using tables to do the multiplications between the weights and the activations. You have really everything you can imagine in terms of how you do this quantization.
Sure, sure. Makes sense. And then maybe one more thing on quantization before we get into other methods. Do quantized networks execute faster than unquantized ones on hardware? I think that depends, but in general, what are your thoughts on the trade-offs between not just accuracy and flops, but accuracy and real execution time, or accuracy and the real energy consumption on a given device?
So we've used a lot of different devices, and we looked at the impact of quantization, of course, in terms of energy consumption, latency, etc. What we've found so far is that, for example, if you're targeting a microcontroller, which could be of use to many people that are doing embedded devices or that would like to have this kind of very, very low energy consuming devices, using quantization is going to help a lot because you're going to have a much less number of operations, and the operations you're going to use are going to be much simpler to implement. So one thing I have in mind right now is that we run some experiments, so using some microcontrollers that is able to support up to 8-bit precision operations natively. And we were able to increase the battery life by a fair amount by using this kind of trick. So definitely it has an impact, depending on the targeted hardware, of course, as you said.
Cool, right.
Okay, so another way to compress an architecture, of course, is to prune the weights. And there's basically two ways to address this problem. So one way is to use what we call the non-structured pruning. So the idea is you can remove any weight. There's no structure in the weight you're going to remove. This is the simplest way of doing pruning. But the problem is that it might be hard in practice to leverage this kind of pruning. Because of course, you're going to have a lot of zeros, but these zeros could be anywhere. So you have to remember what weight is kept and what weight is a zero. So let's say, just to have a rough idea in mind, if you want to benefit from this kind of non-structured pruning, you have to achieve rates of pruning that are above 90% for sure, and in many cases above 98, 99% of zeros if you really want to benefit from it. Otherwise, you're going to have more increase by retaining which weights are zeros and not than just storing the whole matrix and having no gain at all. So another way to do pruning is to use some structure in the pruning. So you're not going to allow any weight to become zero and any weight to remain non-zero. So you're going to say, I want to have very structured zeros that are going to appear in my convolutional layers. And for example, one very efficient way to compress an architecture is to remove entire filters from the convolutional layers. If you remove a filter, it will have no cost. Because you can basically just remove it from the architecture. It's free. You have a smaller architecture, and you do not have to retain the fact that there was a filter before and it was non-zero. So you have a range of possibilities from non-structured, which is hard to leverage but very efficient in terms of the pruning rates you can achieve, and very structured pruning, which is very, very easy to benefit from, but you cannot achieve outstanding pruning rates using this kind of techniques. So I think one of the seminal papers about pruning was a paper by NVIDIA in NeurIPS 2015. I think the title of the paper was something like learning both weights and connections in deep neural networks. And they showed that they were able to remove about 90% of the weights in AlexNet with no impact on accuracy. Again, 90% of the weights on AlexNet is not that impressive because it's AlexNet. And also, this is a non-structured pruning. So 90% of the weight, I'm not sure you can benefit from it. Maybe there are some very specific hardware that could benefit from this kind of very sparse matrices. But let's say that for the mainstream type of hardware, you could not benefit from it. Of course, there's been a lot of works afterwards to try to improve on it and find better ways to identify which weights are important for the decision, which weights are not. And basically, there are two main directions for that. So there's one direction, which is to exploit the amplitude of the weights. So the rationale is that if the amplitude is big, then probably it's an important weight for the decision. The other possibility is to look at indirect measures of the importance of the weight. For example, you can backpropagate the importance from the output to the weight. You can look at the entropy the weight is causing towards the distribution of your activations, etc., etc. It's worth to say that most of the recent papers, they are targeting structured pruning, and a lot of them are actually trying to remove entire feature maps, which is a very efficient way of doing pruning, again, because you do not have hidden cost in trying to remember which feature is removed. You can just basically remove it, and it's free of charge. So it's very efficient in terms of reducing the architecture cost. If you look at the tables in the papers, you're going to see these kind of results where here you have different methods that are being compared. You see that the datasets are CIFAR10, CIFAR100, and ImageNet. And the architectures they are using are quite competitive. So it's ResNet kind of architecture. So ResNet is a good compromise between memory and accuracy. You see that the baseline accuracy and the pruning accuracy are going to be very similar, which is quite good because then you say it's fair to compare these two. And the pruning ratios they obtain are not super impressive, but still in some cases you are able to achieve a reduction by a factor of 4 of the number of parameters in your architecture. There's one thing that is not completely fair though. If you take, for example, this table, when we looked more closely at the way they obtain the performance they report, basically what they do is they train the baseline. And once they finished training the baseline, they fine-tune the baseline using their pruning method. So they add extra steps, extra epochs to the training process. So it would be more fair to continue training the baseline for the same number of epochs. So then these two columns are compared with the same training procedure. And actually, if we do that, we observe that we have so small increase in accuracy for the baselines. And for example, with ResNet 56, we are able to go as up as almost 96% of accuracy. So in the end, you still have a small drop in accuracy, even though it's not explicit in this table. Just to advertise a bit about our work, we introduced 1 year ago another way of structured pruning. That's called shift attention layers, and the archive link is here if you're interested. And basically, it is a very interesting pruning method because not only it prunes and it reduces the amount of memory you need, but also it transforms the convolutions into simple multiplications. And I'm not going to go into the details now because this is not the purpose of this talk, but if you're interested in a pruning method that is very beneficial also to computations, you should definitely have a look at this paper.
Hey, Vincent, just quick reminder, we have about 15 minutes left in the hour.
Okay, I'll be fast then. Thank you, Davis. Okay, so another way to compress an architecture is to basically identify portions of the weights that are very similar and to make them just point to the same location in memory. So this is what we call clustering weights. So a paper that was quite influential in the community that was published in 2015, which is called Deep Compression, is basically a mixture of different ingredients I presented before. So you have pruning, you have quantization, you have this clustering I was talking about. You also have Huffman encoding in the end. We'll see in the next slide that we are not that convinced that deep compression is a very effective compression method yet. A very, very interesting paper I strongly recommend to anyone that is interested in clustering weights is called Deep K-means. It was published 2 years ago, and basically it introduces relaxed K-means regularization during training that makes you the job very easy at the end to just basically identify different portions of the network that looks extremely similar. So again, as I said, we're not completely convinced about decompression, even though they report results where they are able to reduce by a factor of 50 the number of parameters. Of course, this is outstanding results, but when you look closely, again, we are working with AlexNet and BGG. first thing. The third line is SqueezeNet. SqueezeNet is quite competitive, so it's impressive that they report being able to divide by 10 the size of the architecture while keeping the same accuracy. But actually, the first step they are using is non-structured pruning. And non-structured pruning, as I said before, it has a hidden cost, which is you should remember which weights are zeros and which weights are not, which, to my understanding, they are not doing in the paper. So achieving a 10 times reduction in the number of parameters is maybe not that impressive considering this fact. For deep k-means, you see that the first line, you have 50 times reduction, which is huge, but again, you have a drop in accuracy, which is 4%. Again, we said 1% costs a lot, so 4% costs an awful lot, so it's not surprising to have addition by 50 times. This last line is quite impressive, though. You have a drop in accuracy that is very limited, and you have 4 times less parameter. So I think it's still interesting to look at this kind of techniques. I wanted to mention a very different way of addressing this kind of problems. In many applications, basically what you are the most concerned about is the energy consumption of your chip. Because, for example, you want to maximize the battery life. And basically, there's a very easy way of minimizing the energy consumption. You can just basically lower the voltage of the chip. If you do that, you're going to introduce errors during the computations. But because deep learning models are somehow stochastic and redundant, it might not be that dramatic to introduce this kind of errors during the processing of an input. So this is something that we've looked in a recent paper, and if you're interested, there's an archive link here. So basically, this is just a simulation. This is a theoretical model of what's happening. So we took a model where we consider that the error rate is going to be exponential as a function of how we reduce the energy of the chip. And if you do that, you obtain this kind of profiles where you see here, we have a baseline architecture on the top right. We have in black here the architecture that we obtain when we shrink down the number of feature maps. And this one is when we shrink down even more the number of feature maps. And the profiles we have in colors here are what happens when you lower the chip voltage. So you introduce some errors during the computations. And you see that this is more efficient than just basically shrinking down the architecture. So for the sake of time, I won't go too much into the details, but we have introduced various ways of making this process even more interesting in this trade-off between energy and accuracy. And an interesting point here is this one, if you can see my mouse pointer, where basically we have about the same as accuracy as a baseline, but we have reduced the energy by about 3 times. And this is just by lowering the voltage of the chip. We did not have to implement anything to the architecture itself or to do any fancy stuff. This is basically a very simple way to achieve better battery life without knowing anything about deep learning, basically. So just to wrap up about what I said. So I said there are plenty of ways of compressing architectures. And if you want to know what is the best architecture for your problem, you should first try to see what happens when you adjust the number of feature maps. So here is an example with the Cypher 10 dataset. So if you take MobileNet and you shrink down the number of feature maps, you obtain this profile. Now, this is a profile for SqueezeNet. And interestingly, this is a profile for ResNet 18. This is interesting because MobileNet and SqueezeNet have been introduced for the specific purpose of being very efficient. But basically what we observed is that if you take an architecture that was not introduced for this specific purpose, but you just shrink it down, you can have profiles that are actually more interesting than these specific architectures. Of course, this is just for Cypher 10, and of course, we're not taking into account the whole complexity of the problem here. We're just interested in a very simple measure of performance. I'm not saying that MobileNet and SqueezeNet are not interesting at all. Of course, they are. But I'm saying that it's not necessarily the best option for your problem. Now, this is what's happening when you're using distillation. So basically, you see that for the same energy or memory budget, you're going to increase the accuracy, or you could say for the same accuracy, you're going to reduce the energy or memory budget. This is what happens with the binarization of the network. So interestingly, you see that this is not as interesting in terms of, so this is memory actually, you should not read energy for this one. This is just for the memory. So the memory usage, it's not as effective as using distillation. But again, when you do binarization, you simplify a lot the hardware in some cases. So you could have huge gains if you could exploit this very specific binary structure. This is what happens with pruning. And you see that pruning does not seem to be very effective compared to distillation when we are targeting aggressive reduction in the number of parameters. But if you can afford to have still quite a lot of parameters, you can actually outperform the other methods. This is what happens with clustering. So clustering has a very strange profile, which is almost vertical like this. And you have to understand that the main difference between clustering and the other techniques I've presented is that clustering is only interested in memory. But basically, when you cluster a neural network, you're not going to change at all the number of operations you're going to need. It's even the contrary. You're going to need extra operations to run it. So this is a reason why you can achieve this very competitive score here, where you have about 95% with a reduction of almost 10 times the memory. You have the same number of computations. You have to understand this. And this is what happens when you reduce the energy voltage, the chip voltage, and so you reduce the energy on your target. And you see that this is something that is quite competitive with the other possible approaches I've presented in this review. Okay, I'm sorry for being so fast, but I want to have a few extra minutes for questions afterwards. So just to conclude a bit about what I said. So yes, it works. To answer the initial question, can we go below the red curve I presented before? Yes, we can. We can take architectures that are very competitive in this trade-off, and you can make them cheaper, less complex, while still maintaining the same level of accuracy. And basically, there are different ways of doing that. You can use quantization, pruning, factorization, distillation. And any of them mainly could lead to good results. This is not, I'm sorry if you wanted me guys to say, okay, this is a method you need for a specific problem. We don't know. Actually, the experience we have is that many of them can work. And it's not clear, depending on the problem, depending on the hardware, depending on a lot of other parameters, which one you should choose. But the thing that I want to insist on is that most of the time you will not have extraordinary gains. You cannot expect to have orders of magnitude in reduction in the memory or computational cost. And if you see a paper where they say that they are achieving this kind of gains, you should be very cautious about the methodologies they use. Are they using an architecture that is competitive? Are they really making a fair comparison? So this is something you should ask yourself. If you're interested only in energy savings, so maybe it's not worth digging that much into the method. Maybe you can just basically look at the hardware itself and just lower the chip voltage. A lot of things that are open to the field now. So the first thing we already discussed a bit before. The problem is that it's very hard to come with a unified benchmark for everyone. Different people have different targets, hardware targets in mind. Depending on the hardware target, you do not have the same criterions, of course. Sometimes you are interested in the number of flops. Sometimes you have to be more precise about the type of operations you're going to use. It really depends. So it's very hard to compare different methods. Really a few papers are interested in compression during training. It's a very, very hard problem. Actually, most of the methods I've introduced in this talk, they are more complex to train than the baselines. So yes, you gain for the inference time, but you have to use more resources during training. A related problem is that it's very hard nowadays to train on embedded devices for many, many reasons. And this is definitely a very open problem. There's a lot of applications out there where you would like to have at least some fine tuning on a chip. And this is something that is extremely difficult to achieve. And finally, I would like to say that, yeah, I'm finishing, Davis. Finally, I would like to say that it's not clear what kind of method you can combine. Some of them, they work very well when you combine them. Some others, it basically destroys the accuracy when doing that. And this is definitely something that you have to keep in mind if you would like to do something like that. So just to thank all the collaborators very quickly. And yeah, I'm going to finish on this slide. Thank you, Davis, and sorry for being so long.
Not at all. I have to say it's hard. I want you to keep. It's hard for me to have to stop. It's just a matter of time because it's very, very interesting. But so thank you so much, Vincent, for the talk. We do have some questions to get to for the end and some time. Quickly before that, we're going to do a quick recap and some reinforcement of some last items here. So again, thank you so much, Vincent, for the talk. Everybody in attendance, please take the 5-question poll to continue the conversation as well on the forums. If we don't cover your question here in the last few minutes, we can cover it offline as well. So again, there's a quick poll. Thanks again to the sponsors, Edge Impulse, Maximum Integrated, SynSense. You can find more information about Edge Impulse's technology here, as well as Maxim Integrated's different hardware portfolio, as well as SynSense, who build ultra low power sensing and inference hardware. So next talk will be Tuesday. I think that's one of the last things to cover here before we can dive into the Q&A. Also, if you want to, just shortly after, if you want to make a quick announcement, raise your hand and we'll unmute you and you can do so. So quickly.
But Davis, if you haven't launched the poll, you need to start that from your screen.
I need to launch the poll. Launch the poll. Okay, so the poll is launched.
Thank you. Okay.
Thank you, Ara. Yeah, perfect. So a few last questions here about the benchmarks. So Vincent, do you need benchmarks that are related to specific hardware like ARM CPU, embedded GPU, or also new data benchmarks? I think you talked about both, but that's an interesting.
Yeah, I really think we need that, and I would really like people to push for the kind of benchmarks. I really think that if you're working for a company that is providing a specific hardware, you should definitely try to push for, let's say, a competitive challenge at the main conference about the specific hardware target you have, and trying to find the best architecture. My experience is that it so depends on the hardware device we are targeting. We really need a lot of these benchmarks. We really need them to be pushed by those that produce these devices. I think it's beneficial to everyone if we do that.
Cool, cool. And one other question before we do the quick announcements. How reproducible were the voltage reduction results? I think it's a really interesting avenue and straightforward avenue. How reproducible were those results?
So I have to insist that these are only simulations, right? This is not something where we actually did the chip and lowered the voltage on the chip. So we used some models that we found in the literature to try to estimate what are the errors that are going to occur depending on the energy. But then once I've said that, this is very, very stable. Basically, every simulation we make, it's about the standard deviation is very, very low. So I don't know if the question was about that, but it's quite stable.
Okay, excellent. Well, so anyone, quickly the concept here, just before we wrap up, if you have any announcement you'd like to share, please raise your hand and I will unmute and you can make an announcement. But again, Vincent, thank you very much for this super, super interesting talk.
Well, thank you everyone, and I'm very sorry for being that long.
All right. Well, again, you can take the things to the forums as well. There is offline, well, online and in the forums as well to communicate. There's lots of slides that will be shared next week. The recording will be shared next week. And yeah, everyone, so thanks so much for joining. And we will see you hopefully in a couple of weeks.